Giglio Power Infrastructure Engineering. Hello everyone, my name is Dr. David A. Giglio Ventura, and in this video I will show you how I, as a multi-physics engineer, applied electrical engineering to solve a complex thermal engineering problem of determining directly the steady-state transient ampacity, including load transfers, for my thesis titled Dynamic Thermal Model for Different Sized Triple Power Cables with Various Loads in Non-Forced Ventilated Tunnels, published in IEEE Early Access on October 2022. I had used MATLAB to program this complex thermal system and used the IEC standard equations to compute electrical parameters such as AC resistance, including the skin effect and proximity effect parameters and the sheet loss factor. Also, I had used the industry-leading text, Fundamentals of Heat and Mass Transfer by Inc. to compute thermal properties and thermal resistances of the system. Conservation of energy was used to solve this complex thermal system. And in this installation, the temperature dynamics of the cable reaches steady state much sooner than the temperature dynamics reaches steady state for the soil layers. In this case, the total heat generated in the cable, including the conductor, the sheath, and the dielectric insulation, equals the total heat transfer out of the cable via convection and radiation in proportion to the temperature difference of the cable jacket surface and the inner wall temperature. In a transient calculation, all of the heat generated in the cables flows into the tunnel wall, and a system of linear differential equations is solved for the inner wall temperature until convergence is obtained. KCL and KVL from electrical engineering was applied to solve ampacity in this complex thermal system. In this system, an algorithm, the conductor temperature is fixed at the temperature limit, which in this case was 90 degrees Celsius, and the ambient temperature was fixed, in this case 20 degrees Celsius. And the Gauss-Seidel method, numerical method, was applied to solve all temperatures within the system iteratively until convergence was reached. In a transient ampacity calculation, the inner wall temperature was solved by solving a linear system of differential equations as mentioned in the previous slide. The output is the inner wall temperature, which is used as the free stream temperature to compute the convective heat transfer and to compute the radiative heat transfer. Here is a half symmetry view of the temperature distribution of a triple power cable to illustrate various important temperatures. The cable surface temperature is higher than the surrounding air and exponentially decreases to a free stream temperature, moving radially away from the cable surface, where in this model the free stream temperature equals the temperature of the inner wall surface. The mean cable film temperature is the average of the cable surface temperature and the free stream temperature, and is used to compute the thermal properties of the air, including Prandtl number, viscosity, volumetric thermal expansion, to compute the Rayleigh number, Nusselt number, and finally the convective heat transfer coefficient and convective thermal resistance. Here is the algorithm to directly compute full load ampacity. The heat generated in the cable equals the heat transferred out of the cable. Apply the initial conditions, then compute thermal resistances, then compute cable losses and use the heat generated in the conductor to compute conductor current. Then solve the linear system of differential equations of the soil layer temperatures to compute the inner wall temperature. Then compute the temperature of the cable layers. Remember, the conductor temperature is fixed at the temperature limit always. If the system is converged, then we have the solution for ampacity, including transient and steady state. If we desire to compute the varied load or the load transfer, proceed to the next stage of the algorithm. Here is the algorithm to directly compute ampacity in the load transfer. Let's say we have cables 1, 2, and 3, and we want to reduce load in cable 2 by fraction x2 and reduce load in cable 3 by fraction x3. The load in cable 1 will increase by an unknown fraction x1, which we will solve for using this algorithm. We apply the initial conditions, then compute thermal resistances and heat transfer, then compute cable losses and conductor current, using the heat generated in cable 1 to compute the conductor current in cable 1, while fixed reduced conductor currents and losses for cable 2 and 3. Then we integrate and solve the linear system of differential equations using all the heat from the system that passes through the tunnel wall and through the soil layers. And we integrate from time equals 0 to any desired time, which could be steady state or time prior to steady state time. For example, 40 years, the cable life, typically for a cable. Then we compute temperatures of the cable layers. And remember that the conductor temperature is always fixed at the temperature limit. We iterate through this process until convergence is obtained. And also, the heat generated in the cable is always equal to the heat transfer out of the cable. There are 6 total trefoil power cables installed in the tunnel and 1 pair of each cable type installed symmetrically in the tunnel. Here is part of the MATLAB code I developed to model the entire thermal system of the power cables in the tunnel to compute directly the steady state and transient ampacity, including load transfers. In the loop of the algorithm presented before, I update all the electrical parameters, which are temperature dependent, including updating the DC resistance, sheath loss factor, and I use the total heat transferred equal to the total heat generated, and the heat generated in the conductor is used to compute the current for this cable. All of the heat from all the cables passing through the soil layers is used to solve a linear system of differential equations to compute the inner wall temperature, which is used as a free stream temperature for the convective heat transfer and is used in radiative heat transfer. When I run this program, I get all of the ampacity of the cables in the tunnel, which are for cable 1, small cable type, 178 amps, for the medium-sized cable, 417 amps, and for the large cable type, 567 amps. COMSOL Multiphysics was used to verify the ampacities computed with the thermal model and to validate the thermal model, which was developed completely using IEC standards and leading industry text, Fundamentals of Heat and Mass Transfer by Increpera, and Fundamentals of Fluid Dynamics by Munson. The ampacities shown in the center of the screen were used in simulations to produce conductor temperature rise plots and temperature distributions of the tunnel system, as shown on the right side here, which has a maximum conductor temperature of 87.9 degrees Celsius. And on the right side here are the conductor temperature rise plots, where all conductors start at 20 degrees Celsius and rise to a maximum value below 90 degrees Celsius, which the maximum permitted temperature rise for the conductor is 70 degrees Celsius, which for these results have about a 3% difference on the conservative side, which is acceptable for tolerances. Also, we can observe the velocity field of the fluid to see how natural convection is taking place, which is caused by buoyancy due to pressure differences in the fluid, where at the bottom of the fluid, the density is highest and is not moving, and in the upper portion of the tunnel, the density is lowest. The fluid is heated, which we observe induced cooling as fluid moves in a circular motion, and also fluid is moving over the tunnel walls, dissipating heat. Contact Giglio Power Infrastructure Engineering if you would like to have full detailed multiphysics modeling and analysis of any complex power cable installation to directly and accurately compute power cable ampacity. Visit our website, www.gpiengineering.com. My name is Dr. David A. Giglio Ventura, and I also have a professional engineering license in Puerto Rico and in multiple U.S. states. Thank you and take care.